Hi, today we are going to present our project for DA626 course on behalf of our team number 16 consisting of me, Shauroja Kundu, Thanish Bolla and Khushi. We have proposed to implement a paper submission venue recommendation system. So, when an author writes a journal or a conference paper, then he or she has to go through the trouble of finding out the appropriate journal or conference venue in which the rejection probability will be the lowest. Also, there are factors like how much will be the publication fee of that journal or conference, or how much time will it take till the first review. And also, sometimes the novelty level of the paper which the author has written does not match with the novelty level the paper accepts. So we have to take into consideration all of these factors when we suggest the most appropriate journal or conference. Because of that, we have proposed this personalized paper submission recommendation menu. So, for training our models, we start with collecting a data set. The data set will contain different papers published in different journals. So, the paper title, the abstract, the keywords, and the journal name will be the each of our data samples. So here we show an example of how the collected data set looks like. So it has an ID and a title, abstract, and also keywords. So there is already some existing work using content-based approach, and we found a GitHub repo where they open sourced the data set containing at least 66 journals, each with at least 14,000 papers. We used, and the topics of the journals are related to computer science, cyber security, networking, etc. So we used that data set for training our models, and also we collected the recent like 2023 2024 papers based on artificial intelligence and computer networks and other domains of system security topics. We have collected till now 110 papers manually by web scraping, which looks like this on the shown in the screen. We will use this dataset for testing, but the publicly available dataset by the other paper for training. So this data is available in JSON format. We will load the JSON file and we'll create the knowledge graph. For creating knowledge graph, we are using a vectorized database called the Neo4j. So in Neo4j, we are showing how we are in the code, how we are loading the data from the JSON file, and this is how the final knowledge graphs looks like. So there are two kinds of nodes, journal nodes and paper nodes. So as you can see, the orange nodes are the journal nodes. There are two kinds of relationships. So when a paper belongs to a journal, so the relationship will be called published in, and there can be other connections also, but initially we started with the knowledge graph structure as follows. So there will be one journal node, and all the papers published in that journal will be connected to that journal node as paper nodes. And all these journal nodes with their corresponding paper nodes will be isolated. There is initially no connections in between the journals or papers from two different journals. So this model can be used as a baseline model, but we have to also incorporate the knowledge which, let's say, an experienced author has about the publication field. So an experienced author knows that which journals have some scope similarity or the research content similarity. So to simulate that experience or the knowledge, we have to introduce some connections between the journal nodes. And so for that, we first calculate the similarity scores among the papers. And we have to select a certain threshold. If the similarity score is above that certain threshold for the papers, then we will establish a graph edge or a connection between the papers, otherwise not. Initially, we also keep the like connections of all the journals as one. So all the journals are connected to each other. Later we will update those connections, but the paper connections, that is paper graph edges, are based on certain threshold. For the threshold, we have tried three different values. If the similarity is greater than 0.5, greater than 0.6, or greater than 0.7. So these are the plots, and we found that if we keep the paper connections, if the similarity threshold is greater than 0.5, then there are way too many connections, and many of them can be spurious or noisy connections as well. So it's like a weak connected knowledge graph. But if we keep the threshold very high, let's say 0.7, then there will be very less connections, but all those connections will be very strong. So we wanted to go to a middle ground between 0.5 and 0.7, so we chose 0.6, but we had an acceptable number of paper similarity connections, which will not even overload the knowledge graph, because if there are too many connections, then the computational complexity will also be very high. So we need not to make the connections too high, as well as we need to keep only the relevant or meaningful connections. So because of that, we kept the threshold, similarity threshold of 0.6. So whenever two papers have similarity more than 0.6, there will be a connection, and the relationship is called similar to. That is how the initial knowledge graph is settled. Now Tanish will go through how we will apply graph convolution network to update the journal embeddings. And these journal embeddings will accumulate the knowledge of all other similar journals in the papers published in. So it will be for acquiring the domain knowledge of that particular research topic.
So once we create the knowledge graph, we extract the adjacency matrix from the graph, where the journal connections and the paper connections are established clearly. And once we have extracted the adjacency graph, we make the train test split by train val test splits by 80, 10, 10%. We do the splits by masking the certain parts of the graph, uh, so that masking it makes the paper connections of the validation and test parts zero, so that they are not part of the graph. So let's walk through how the GCN is structured over here. The GCN is set up having convolutions between the embedding dimensions of size 384 between the journals and papers, and of two convolutions of the same size, where the embedding size is preserved 384 to 384. It is done so that the GCN will embed the message of the neighboring nodes and collect the information from the neighboring nodes and pass it on to the future node. So there are operations such as this, which will do that. And after that, the paper embeddings are set fixed in this. We do not change the paper embeddings in the training process. So once we get the we get the journal embeddings out of the after the convolution operations are performed. We While training, we use the cross entropy loss, so that the journal embeddings are updated during training and the paper embeddings are set fixed during the backprop operation. So while training, the journal embeddings are used to calculate the top one predictions for the papers. So the cross entropy loss is used, where we get the loss function, and the journal embeddings are the weights of the GCN, which will be changed during backprop. So after training, during training, we use early stopping, which stops at 460 epochs, and we get a good train accuracy of 81% and validation accuracy of 79%, which is really good. And once we have done that, on the test set, when we measure the final evaluations, we get a top one accuracy of 78% using GCN, and top three accuracy of 88%, and top 10 is really 96%, which is really good for recommendation systems in general. And so, what is the benchmark of comparing these GCN models? So, the benchmark use something called as the average embeddings of the journals, which Sauraja will walk through what is the benchmark embeddings and what are the results of the benchmark embeddings.
So the average embedding model is when we replace each of the journal embeddings with the average of all the paper embeddings published in that journal. So one thing to note here is that we created the embeddings using a sentence transformer model, using a pre-trained model. But in some existing works, they have used different versions of transformers, bidirectional transformers, and also mixture of transformer encoders to create those embeddings. So first we compare the top 1 to 10 accuracies of the both the benchmark model as well as the graph convolution model, and the table looks like this. So we see that for the GCN model, over all the both the train and test sets, the accuracies, the top 1 to 10 accuracy, the top 1 to 10 NDCG values, the MRR and the MAP, all these evaluation metrics are giving much higher values. So MRR is mean reciprocal rate, and MAP is mean average precision. So after we have done this ablation study of the model without GCN, the benchmark model and the model with GCN, and we observed that the GCN model is performing way better than the one without the GCN. Next, we try to introduce a novelty scoring algorithm. So the idea is when the abstract and the title of the paper, which is to be submitted, we will judge the novelty of that paper by that abstract and title. And how do we judge the novelty? We consider that we have sufficient number of journals in that particular research topic. Let's say I'm submitting a paper on computer networks, then there are let's say around thousands of papers and there are many journals publishing on the topic computer networks. So, what we can do is we can find the similarity. We can calculate the similarity of this paper with all those existing papers. But since there are too many papers, the computational complexity will be too high. That's why we first calculated the similarity of that paper with all the journals, and then after sorting, we picked up the top 5 most similar journals. We can keep it top 3 or top 10, whatever we want, but we did it with top 5 journals. And then all the papers published in those top 5 journals will be used to calculate the similarity with this paper. So there will be less number of computations, and uh, if this similarity score is less than a certain threshold, then we can say that this paper is quite novel. Why? Because all the papers in this particular research topic are not matching with this paper to be submitted. By plotting the histograms, we found out that if we keep the novelty scores as follows, that if it is less than 0.15, then it is very novel, and then if it is between 0.15 to 0.22, then it is more or less sufficiently novel. So this is more or less innovative. Then if it is 0.22 to 0.28, then it is some incremental research, and if it is more than 0.28 similarity, then it is just not innovative, and so it is suitable for a Q4 journal. And that's how we also divided it through all the 4 quartiles: Q1, Q2, Q3, Q4 journals. And these are the pie plots. We also see that the red one in the pie chart is the most novel papers. The blue one is for Q2, the green one is for Q3, and the yellow one is for Q4 journals. And so next we have deployed our model in a website where we will first give the recommendations, the top K recommended journals when the title and abstract of a paper is submitted. And we also suggest that depending upon the novelty of that submitted paper, in which category journal is it most suitable to. So Thanish will now demonstrate the website.
Let's go through a quick demonstration of the website, which is deployed on Streamlit Cloud. Uh, so this is the website you have, which I have loaded currently. And let's take a quick example from the 100 recent research papers that we have gathered recently by through scraping. And let's take this title and abstract of this paper, and let's see how this works for the latest research papers. Okay, let me take the title and cut it out and put it in the title. Yeah, okay. I think, yeah, we can even toy with the number of recommendations we want. I said, let us set it as 6, and let's see what are the journals it recommends. Okay, so we get the novelty of the paper, and it says you are good enough to submit in the Q2 journals or conferences, and it's based on an analysis of the 2,500 papers. So it compares those abstracts of the 2,050 papers with this abstract and sees how different or novel it is. And then you could see the recommendations it gave on computer communications. Predominantly, the journals we had are based on CS and networking, and yeah, it gave some communication system journals and the networking journal. The true journal of this is the IEEE ASEAN transaction on networking, and you can see it came up in the third spot, I think, which is really good for a recommendation for the latest research papers. And yeah, that's our demo.
Thank you.